Welcome back to ECE 220. Hopefully you've read the novel before we've started. There's quite a bit of information on the screen, a lot of announcements. We won't be here tomorrow, but you will need to submit your lab number 5 report if you're in Group A. Group B, you still need to be going to lab today, and everybody's homework is due by tonight for homework number 13. And then when we come back on Monday after the break, it will be a review lecture for exam number 4, and exam number 4 is occurring on Thursday, a week from 2 days from now. I was going to say a week from tomorrow, but we're not Wednesday. This is Tuesday. So try to remind me if I forget when I look up at the clock and see 7:30 and I'm not even sure what day it is or where we're at. But hopefully we will all be able to do what we want to do today, which is work through some transformer problems and applications. Question? So next week, I'm trying to think where we are, but next week we have a review lecture on Monday. Then we'll have 2 more lectures between that and the exam and that won't necessarily be review. It will be, not sure what it'll be. It might be worked problems. I don't know how far we are going to get today on these transformer problems. I know we need to still talk about RMS. How do we find root mean square value for a generic periodic waveform? And we'll squeeze that in somewhere. And then a couple of weeks from now, in the last week of class, I think those Monday and Tuesdays will be review. Now I've confused everyone probably, but those will be review for the final. Your last day of class in the fall semester is the 11th of December. The 2 days preceding that, the Monday and Tuesday, we will be reviewing for our final in this class. Hopefully we're sort of aware of what's happening when and where. But if you're in Group B, make sure and go to lab today. You hopefully have already completed your pre-lab. And don't forget to complete homework number 13, which is RLC circuits. And that's the last homework assignment topic-wise for exam number 4. Exam number 4 will be containing, what did we decide? Homeworks 9, 10, no. I don't remember, but not for homework assignments 14 and 15. It's not chapter 9 for exam number 4. Exam number 4 is essentially first order and second order circuits, RL, RC, and RLC circuits. That's exam number 4. Today we're back in chapter 9 at the end of the topics for the semester, and as I had indicated, I wanted to try to go through some problems dealing with transformers. And before we do that, let me just give you some more examples of how you might utilize a transformer in an isolation situation. We talked about different ways or different applications for transformers. Let's now look at 3 different ways that you might see a transformer used for isolation purposes. One is for safety. So now you have this distinct separation between conductive current in a circuit. You might now have a primary side on the left And then you might be trying, this is sort of a wall wart illustration in terms of, I've tried to illustrate, you have a transformer only works with time varying waveforms. On the primary side you have some AC signal. Then on the secondary side you also have an AC signal, but there's no wires conducting that current from secondary to primary. It's all induced voltage in the secondary. You then rectify that, which means you can make everything positive and then maybe filter it with a capacitor, and the red line is supposed to indicate a more DC type waveform coming out, which is what your wall wart is typically doing. You plug it in, you have 120 volts at the wall, but then coming out you may have 12 volts DC that you're plugging into your device that you're powering, whatever that device might be. So there's no conductive coupling, there is magnetic coupling, and that now allows you potential uses for safety reasons. This one we talked about last time. This is now, since we're playing on the fact that this transformer only passes sinusoidal, or not sinusoidal, but time varying waveforms. Typically they're sinusoids. If you now had some amplifier that had DC and AC components, you've essentially removed the DC component on the secondary side, and now you simply have this alternating current on the secondary side that you can start amplifying. So this second application removes DC waveforms. And finally, here's this is kind of the commercial before the main event or the main feature. One more application. You might now use a transformer to step down voltages. If you now have a high voltage source that you want to monitor, you can now do that maybe with lower voltage equipment by pushing this or converting this high voltage waveform down to a low voltage waveform by a step down transformer, where now you might be working with 120 volts AC, and this is sort of what's happening between the high voltage transmission lines and your home at wherever you're at, in terms of you might be, before it gets to the neighborhood, it might be at 13.2 kilovolts. Then it gets stepped down a couple of times, and eventually now you are seeing it in your house as 120 volts AC. Let's now see if we can use some of these ideas that we talked about last time. Current ratios, voltage ratios, impedance, reflection. What does the impedance look like to the source after being reflected through this particular transformer? And here is one where we are trying to match maybe this high fidelity amplifier, maybe a tube based amplifier that now has an output impedance of 192 ohms. And you want to now drive a loudspeaker that has an input impedance of 12, and you want to now select alpha, the turns ratio, to allow the output impedance to look like, or the input impedance of the speaker, when you reflect that back, you would like it to now be matched to the impedance of your amplifier. If we are now, what's the condition that we want for matching? What relationship are we looking for if our Amplifier has an output impedance of 192 ohms. What would be the value of impedance that you would like to see effectively at those nodes? What would you like to see? So now we're saying we are trying to have a circuit. Here's our amplifier. We have its impedance, which we've said is 192, and we want to figure out what we want Z sub R to be. What does it mean for the impedances to be matched? Hopefully that's clean in terms of a description of what we're trying to do. We want to make Z sub R appear as if it's 192 by the selection of those turns on our transformer. And last time we actually derived the relationship between the reflected impedance and the load impedance, and that was by dividing it through by alpha squared, where alpha was your turns ratio. In this case, then, it is desired to have 192, and this turns ratio was n sub 2 over n sub 1, where that was the secondary turns over the primary turns. This is now what we need for our impedances to be matched. We're trying to reflect that 12 ohm speaker impedance through the transformer. We now take 12 divided by alpha squared, and we want that to be matched to the impedance of our amplifier, which is 192. This now simply says that we need to solve for alpha squared, or alpha. We now have alpha squared is 12 over 192, and 192 is nicely divided by 12 by a factor of 16, which now allows us to say that alpha is 1/4. And this is now this n sub 2 to n sub 1 ratio. What kind of a transformer is that? Step up or step down? N2 is less than N1, so this is in fact a step down. You're trying to step down the voltage to transform the impedance seen by the amplifier to make it appear as if it's 192 ohms. So this is actually a step down transformer, where the step down refers to the voltage is now being stepped down. Let's look at the power in the two different scenarios. Compare the power that's actually delivered to the speaker in the two different cases. Case 1, let's say that this is now without the transformer. In this case, we have our amplifier, whatever it was. We didn't really need to know. We'll just keep it as V Thevenin. Here is the impedance of that amplifier, 192. And now without the transformer, if we just connect the speaker, we have a 12 ohm load attached to our amplifier. What's the power of the load? This is a review for the final. I promised I would do review for the final some other time, but we're actually doing it now through this problem. There's many different formulas for power. You could say, oh, let's just do I squared R, where R is this load resistor, or I squared is V Thevenin over the total resistance, which is 192 plus 12, which gets us up to 204. There's I squared. And we're multiplying that by the impedance of the speaker, which was 12. If you now do the 12 divided by 204 squared, you'll find that the P load in this situation is 288 V Thevenin squared microwatts. Again, we're not worrying about V Thevenin, and let's just keep it as a magnitude. What's the other scenario? Now with the transformer, we haven't changed the amplifier. But now what does the load look like? That was this Z sub L over 1/4 squared, or 16 times 12, which is 192. So here, if we say, okay, what's the load now? Power at the load, it's I squared R again. But now what's I squared? It's now V Thevenin over 192 plus 192, which is 384 squared times 192. So that in this case, the load power, if you do the 192 and divide it by 384 quantity squared, ends up being 1,302 V Thevenin squared microwatts. And what we're trying to compare now is which one had the most power at the speaker. And we're now comparing 1,300 to 300. So now by using the transformer to match the impedance of the speaker with the impedance of the amplifier, we actually have delivered more power to the speaker by a factor of 4 or more than 4. So that's how we would benefit then from using that transformer to match the impedances. Let's look at another example. Suppose now that you have this ideal transformer. N2 is now bigger than N sub 1, so it's a step-up transformer. And we want to now find the primary current phasor, I1, and the output voltage phasor, V sub 0 bar. Can we find I1? Or how might we do this? Do you see that you can essentially get rid of all that mess with the transformer if you simply reflect the 20 ohm resistor to the primary side through the transformer? Can we now see what this Zn is, or the equivalent impedance seen at, let's say, nodes A and B? That resistor looks like something on those terminals or those nodes, and we can actually simplify this problem if we could now find Zn, or Z equivalent, at nodes AB. And we now know how to do that. Z equivalent, or Z sub AB, is what? What's our formula? If we call this Z sub L for our load resistor or load impedance, we have Z sub L over alpha squared. And alpha squared or alpha is 2 over 1, or 2. We square that, we get 4. So now we effectively have this circuit. We now have 120 at 0 degrees. We have 4 ohms here. We have minus J6 here. And now we have 5 ohms there. And we were asked to find I1. And now this is a fairly straightforward problem. We just have to use Chapter 9 material to find this. What is I1? Well, now I1 as a phasor is 120 at 0 degrees divided by 4 minus J6 plus 5. And if you do the math, you end up with this having a magnitude of 11. And did I say this was in RMS? And we'll learn more about RMS, but this is now volts RMS, so this current is going to be an RMS current, but we also have a phase now of 33.7 amps RMS. That's now the first half of our problem. We wanted to find the current on the primary side of our circuit. And we've now found that to be 11 amps at an angle of, or a phase of 33.7 degrees. We also now are asked to find V sub 0. Ouch, that's on the other side. Do you see that that's not that? But if we came back up here and said, oh, if we could find I sub 2, then we could use I sub 2 times R load to find V sub 0's phasor. And with an ideal transformer, we can actually relate the current in the primary coil to the current in the secondary coil. So let's make that connection right now. Notice that in this case, I sub 1 and I sub 2, we need to see how they are oriented relative to the dots. Do they both go into the dots? Does one go in and one go out? Because that influences the sign relationship on our current ratio. I1, what's that doing relative to the dot on the primary side? It's going out of the dot. What about I sub 2? It's also going out. So what does that mean? What does that mean? They're both doing the same thing relative to the dots. These are both leaving the dots. What's that do to this amp turns relationship? Positive or negative? Since they're doing this, or both doing the same thing relative to the dots for the currents, that says we now need to negate the amp turns relationship. Or this now says that if we said, oh, I sub 2 over I1, phasor is now minus N1 over N2. And we know what N1 and N2 were. N1 was 1 and N sub 2 was 2. And we just found I1. That allows us to very quickly find I sub 2. Now we know I sub 2 is minus 1/2 I sub 1. And I sub 1 was this 11.09 at an angle of 33.7 degrees. What's the phasor for I sub 2? Well, the magnitude is just 11 divided by 2, so that's 5.5, and if we get more digits, 4.5. What do I do with the minus sign? You could either do plus or minus 180 degrees. It's the same. We're just changing it by 180 degrees. But what's the convention? Which one would we use? Plus 180 or minus 180? We use the plus or the minus in such a way that we get a net angle or phase that's between or less than 180, plus or minus 180. So we want it to be in magnitude less than 180. We subtract 180 from 33.7 and we end up then with a minus 146.3 degrees amps RMS. That's I sub 2. That's not quite the answer we need. We needed the voltage dropped across that resistor, and that's now just the 20 ohms times the phasor current on the secondary side. Or this now is 110.9 at an angle of minus 146.3 degrees volts RMS. And if you wanted to go back and say, well, how's the output voltage compared to the input voltage in this circuit? The output voltage had a magnitude of 110. So we're dropping some voltage through all of this process, and the phase is quite different. We've almost changed the sign between the output voltage V0 and the input voltage. It's now delayed by a phase of minus 146.3 degrees. If it had been minus 180, it would just be the exact opposite phase of the input voltage. It's not quite that extreme. Let's see if we understand this relationship between voltages and phase relative to going through this transformer. Here's our quiz. So now we're going to have, and maybe I should have labeled those 1, 2, 3, and 4, but now A is 1 for finger, B is 2, etc. I now want you to tell me which of these patterns, 1, 2, 3, or 4, A, B, C, or D, is more likely to be correct based on this ideal transformer configuration. And I think I've tried to be consistent. Blue is V sub 1 and red is V sub 2. And they're time varying, they're sinusoids. Are we ready to answer? All right, at the count of 3, show me 1, 2, 3, or 4 fingers to indicate A, B, C, or D. 1, 2, 3. All right, we're not very clear on this one, are we? If I averaged that, we would be kind of a, I don't know how we would average. I want one answer, and it's not. So, what's the relationship magnitude-wise? Which one should be bigger? So can we eliminate half of these? Which voltage should be bigger? Is this a step up or a step down transformer? Or we could say, you know what, I don't know what he's talking about, but I do know my volts per turns are the same. So I do know that this V1 over N1 is equal to V2 over N2. Now I have to figure out the sign. What's the sign on that turns ratio? Is it positive or negative? Do the dots have the same polarity labels on both sides? No. So now this is going to be a great day. This is now going to be negative. And what does that mean? If I solve for, let's say I solve for V sub 2. Now I have that as minus N sub 2 over N sub 1 V sub 1. Does that now tell us the relationship between magnitudes? N sub 2 is 2, N sub 1 is 1. So V sub 2 better be twice as big as V sub 1. Which of these sketches did I do that right? No. I told you this was going to be a great day. Is that what it is? No. What am I doing? V sub 2 is now N sub 2 over N sub 1. Oh, That's why I labeled these different than my original notes. That's why I'm getting confused. So this is now V2 needs to be bigger than V1, correct? That's why I was misled by your fingers. I was expecting a different answer. So V2 now needs to be twice as big as V1. So now this one is a possibility and this one is a possibility. Is that true? Is the red twice as big as the blue on either of those? And now what's my sign relationship? They are now flipped, aren't they? They're 180 degrees different. So by a process of elimination, isn't that the right answer? The A. Okay. Let's now, and I don't remember now how the fingers were being shown, since I was thinking I should be seeing one set of digits and my notes were completely against that. So, is this clear on how we obtained the picture that we obtained? What kind of a transformer is this? Step up. So now that puts us in the upper half, and the fact that the dots were labeled differently said that our polarities were opposite of each other. Since we're doing such a good job with all of this reflection, let's reflect twice. Now we have to, or what the question is we want to know what's the impedance, the effective impedance seen at terminals A, B after reflecting this load impedance through two different transformers. And now we can simply do this in stages. Suppose we first say, let me look at this. Let me call this Z sub 1 as an impedance. What's Z sub 1? I can write down the formula. Z sub L over alpha squared, but what's alpha squared in this case? N1 is equal to 1, N sub 2 is equal to 25, so that alpha is 25. Or we now can say that this is 1 over alpha squared times Z sub L, which was 200 plus J 150. And 25 squared is 625, or maybe we just keep it as 25 times 25. And that allows us now to write this as 8 times 25 plus J 6 times 25. And let's just keep one of those 25s around. So now Z sub 1 is 8 over 25 plus J 6 over 25. We okay with that? Now we've made it this far. We now need to reflect that even further to get Z sub AB. Z sub AB is now Z sub 1 over, and let's put a party hat over on it, alpha hat squared. Since we have a different turns ratio, N1 hat, make sure I'm giving you the right numbers, this is 50, and N sub 2 hat is 1. So that alpha hat squared is 1 over 50 squared. Or this is now 1 over 50 quantity squared times 8 over 25 plus j 6 over 25. So that 50 squared comes upstairs. In the form of 50 times 50. And we had an 8 over 25 plus a j 6 over 25. So that one of those 25s can go away. And now we actually have 4 times 25 out front, or 100, times 8 plus j6. Or this is now 800 plus j600, which in fact was just 4 on the original impedance Z sub L. Meaning, after going through those two transformers, the net effect seen at nodes A, B is just to scale the original load by a factor of 4 to yield 800 plus j 600 ohms. Getting a feel for these reflected impedances. Now that we've reflected a few, let's try a different example. Let's do some mesh current analysis. I know everybody likes mesh current analysis. So let's do a mesh current analysis, and now we have a common node, and now we have a tail of an impedance below the ideal transformer. So this is a little different scenario. And to make it even more different than what I typically do, I'm going to now have my currents. I'm going to label those currents not going in the same direction. Maybe on the final you'll have some labels that you're not used to. So let's do that here. Let's say this is I1, primary current. And now let me say that I2 is that way. What else do I probably need to introduce in this diagram? The V1 and the V2 on the primary and secondary sides. Let's put those in, and let's say that now somebody says, you know what, I want to play nice with my dots for my voltage, so let me put the positive sign on the primary side dot, and let me let V sub 2 also be labeled such that the positive terminal on V sub 2 is on the dot. What's I1 doing to the dot? Entering or leaving? What's I2 doing? So what does that tell me about my turns ratios? They're all going to be positive. My voltages are matched up with the same sign on the dots, and my currents, one's doing one thing and one's doing the other, so those are now positive. So my transformer relationship for the ratios now allows me to say that V1 over N1 is equal to V2 over N2. And if I solve that for V2 over V1, that's positive N2 over N1. Likewise, on my amp turns, I have, and these are phasors, I1 N1 is equal to I2 N2, and the dot property on my currents, one enters, one leaves, that says I have a positive polarity. I can now say that I sub 2 as a phasor over I sub 1 as a phasor is now N1 over N2. So if I need those, I have them. If I want to convert between V's or I's, I have the relationship in terms of my turns, and I know what those are. N1 is 2, and N sub 2 is 2. So let's do a mesh current analysis on the first mesh. Starting in the lower left, what's that going to yield? I have a gain through the voltage source, so that's a minus drop, a minus 120, plus 20 I1, plus V1 bar. I just worry about the voltage dropped across the cores, and then I have 30 times what? Now, because of the way I labeled my currents this time, they're both going in the same direction. It's 30 times I1 plus I2. It's not the difference between my currents this time. So my KVL in the primary side is now minus 120, and I'm just going to forget the angle because it's 0, plus 20 times I1 plus V1 bar plus 30 I1 bar plus I2 bar is equal to 0. What about the second? Well, which way was I2 going? It was going this way. What about the second mesh? Do you see in this case, if I start in the lower right-hand corner, it's going to be 10 I2 minus V2 plus 30 I2 plus I1. What did I just say? I said 10 I2 plus, actually I said minus, didn't I? Minus V sub 2 plus 30 I1 plus I2. Now, I was trying to find, did I even say? I wanted to find V naught. So it might be helpful if I eventually find I2. This set of equations right now contains 4 unknowns, and I have 2 equations. But through my voltage ratio and current ratio, I can eliminate 2 of those unknown variables. Since I'm looking for I2, maybe I better eliminate I1 and V1 and solve for V2 and I2 from these 2 equations. Once I have I2, then I can use that to find or compute V sub 0. V sub 0, in fact, is going to be what in terms of I sub 2? What's Ohm's law telling me with the passive sign convention? It's going to be V0 bar is minus 10 I sub 2's phasor, because of the way that it's been labeled and the way that I drew I sub 2. Well, you know, before the tryptophan kicks in, see if you can solve that. Maybe it'll build up an appetite for the Thanksgiving recess. See if you can now find V sub 0. Do you want the answer? Who knows if it's right? But here, let's just say that, let's just humor ourselves and say this is now minus 400 over 55. And you can figure out how to account for the minus sign in terms of the phasor, the angle. But see if you can come up with that, and maybe we'll check answers when we come back from break. Enjoy your break.